What's up, folks? This is Ref Barry Brown, University Physics graduate student. Today, I welcome you to the next episode of Quantum Field Theory, or Advanced Quantum Mechanics. So, today we're going to begin the process of second quantization, one of the most exciting things in quantum field theory. Well, all of it is exciting, but this is the beginning of the journey. This is the beginning of the golden road. So, what is second quantization? Well, what is first quantization in the first place? Well, first quantization is when we figured out that particles behave like waves. For example, an electron has some kind of a de Broglie wavelength associated with it, right? So this electron can be localized by some kind of a matter wave. We call this a de Broglie wavelength for the electron. And so every particle has this kind of a wave duality to it. Now, second quantization is when we came up with the idea that waves can also behave like particles. For example, the electromagnetic wave can behave as if it's carried by a particle called a photon. Lattice vibrations or sound waves behave as if they're carried by phonons, which are these little quantum bits of lattice vibrations. So not only can particles behave like waves, that was first quantization, but waves can behave like particles. That's second quantization. Now you might say, okay, haha, very revolutionary. You just flipped the statement and now you have a whole new theory? What's all that about? Well, turns out that this is actually a very profound statement. And to understand the meaning behind the statement, we have to start with the simple harmonic oscillator. That's where everything begins. Or another way to say it is the spring. Okay? It turns out understanding how springs work, which is a basic Regents level physics concept, if you can understand how quantum springs work, then you can understand quantum field theory. So let's begin there. So first thing I'm going to do is start with the picture of a spring. Okay? This is a spring. Okay, great. So what is the characteristic of a spring? Well, the spring is like this. If you push the spring in one direction, then it has a restoring force in the opposite direction. And in fact, the restoring force is F is equal to kx, right? This is what a classical spring behaves like. And we know the equations of motion for a classical spring are some kind of a sinusoidal, right? The spring is going to bounce back and forth, left and right, right? Those are the equations of motion of a classical spring. But what about a quantum mechanical spring? What do I mean by a quantum mechanical spring? For example, if you have a nucleus here with protons and neutrons, and then an electron orbiting around the nucleus, we could approximate the connection, the attraction between the proton and electron to be as if the electron was connected to the nucleus by a spring. Now, of course, that's not what's really happening, but it is a good first order approximation. And why is that? Because to a first order approximation, any potential, any arbitrary potential can be modeled as a simple harmonic oscillator. Okay, well, for example, this crazy looking potential right here at this equilibrium point, it can be modeled as a simple harmonic oscillator, something like that, right? And why is that? Why do we care about the equilibrium points? Because that's where a physical system will typically be in, right? A physical system will typically be at the minimum, at the equilibrium of its potential. And in those equilibrium points, we can approximate the potential as some kind of a simple harmonic oscillator. And so that's why this model of a spring is so useful. It's so omnipresent in physics. So if you can understand the simple harmonic oscillator, then you can begin to understand the process of second quantization. So now let's actually start the real math. I mean, this was just an intro. Let's really start the physics. And let's start with the simple harmonic oscillator in quantum mechanics. So here's what I'm going to do. I'm going to put a spring here, and I'm going to put an electron on one end of the spring. Okay, so the first thing I'm going to do is write the Hamiltonian for this system, right? We know that the Hamiltonian for this spring is going to consist of a kinetic energy term, right? P squared over 2m. And then we're going to have a potential energy term. Now, what's the potential energy of a spring? If not 1/2 kx squared, right? 1/2 kx squared. So k is the spring constant of the spring, and we can write that as this. Oh no, oops. The angular frequency of the spring is omega square root of k over m. So we can express k as what? We can have m omega squared is equal to k, right? Make sure that I did that right. Yes. So now I can replace k over here in my Hamiltonian by p squared over 2m plus 1 half m omega squared x squared. Okay? Very good. So that's the Hamiltonian for a spring. Now, what are we going to do? Well, we want to figure out the energy states, the eigenstates of this quantum mechanical spring. So how do we do that? Well, somehow we have to solve Schrodinger's equation to figure out the Hamiltonian's eigenstates, right? Remember that Schrodinger's equation, right? The time-independent Schrodinger equation says h psi is equal to e psi. And our goal here, our goal now, is to figure out what these E sub n's, these energy eigenstates, are equal to, okay? So what do we have to do to figure out the energy eigenlevels? Well, somehow we can factor this Hamiltonian out. So there's a very nice trick we can use to solve for the energy levels from here. Let's do that. Let's take a look at that trick. First thing I'm going to do is factor out. I'm going to factor out 1 half m omega squared. So what's that going to give me? Well, that's going to give me p squared over, now let's see, I have an m over here, so I need a m squared here, an omega squared here, and then I have just my regular x here. So let's just make sure that this works out as intended. So I have m divided by m squared, that just gives me p squared over m. I have my factor of 2, and omega squared cancel, and as intended, I reproduce my original Hamiltonian, right? So this does indeed factor correctly. Okay, so great. Now what's the next step? Well, this should be x squared. So what's the next step? Well, this looks suspiciously factorizable if you use imaginary numbers. Okay, so we can write this as 1 half omega squared, and then we can frame this as what? I m squared omega squared p plus x, okay, this is an operator, times minus I over m squared omega squared p plus x. Okay, so that should be pretty straightforward, right? I mean, we just factorized what looks like a integral factorizable term, polynomial. But this is actually not true. Okay, this does not work out because x and p do not commute, right? Because when you try to measure the position and momentum of a particle simultaneously, Heisenberg's uncertainty principle says no, you cannot do that. Okay, because the commutation of x and p sub x is, in fact, let me be even more general, x sub I and p sub j is IH delta IJ. No? Right? So this is actually not going to factor out like this. Why? Well, let's go ahead and FOIL it out. When in doubt, FOIL it out. Let's see if this works out. So I have I times I is -1 times that negative gives me 1. So I have 1 over m squared omega squared p squared. Okay, looking good so far. And then let's multiply these two terms. So I've got I over m squared omega squared px, and then minus I over m squared omega squared. And then here, okay, I have x times p. Now that's not the same as p times x because again, they do not commute when measured in the same direction. And then finally, I have my x squared term. Okay, this was a bracket. Let's be consistent here. So that is the problem here, right? The problem is that these two guys do not commute. Px and xp are not the same. I cannot just cancel them out, right? So what can I do? Well, I can go ahead and factor out something. So let's do that. Let's do it. So first of all, what do I have here? That's just my regular old kinetic energy term, p squared over 2m. What do I have here? That's my spring potential energy, half omega squared x squared. And then here, if I go ahead and factor out I over m squared omega squared, I'm left with, let me put a parentheses here, px minus xp. But hey, what is px minus xp if not the commutation of the momentum and position operator? So this right here, I can replace with the commutation of the momentum and position operator. Okay, so let's just write down the remainder of our Hamiltonian, p squared plus 2m, 1/2 m omega squared x squared. All right, and what is the commutation of p and x? Well, we just wrote it over here. If you wanted to really prove it, you could, of course, rewrite p as IH bar times the nabla operator, and you could go through the process. But anyway, it's IH bar delta ij. So what is it going to be here? Well, we flip the commutation here, right? This is px, so this is going to be minus IH bar. Okay, so I times I is -1 times that negative is just going to give me an overall positive sign here. So this is just going to be H bar, right? So all of this to say that I simply have H bar over omega squared right here. Okay, now remember that I multiplied by omega squared and m squared throughout. So this m squared omega squared is going to die out. I'm just going to have a factor of 2 over here. Okay, so this is what my final Hamiltonian reduces to after I try to factor it like this. So as you can see, this right here is simply my original Hamiltonian, right? It's my kinetic plus potential term. So this is my original Hamiltonian, but I've got this ugly little factor of h bar over 2, right? So if I just remove that factor of h bar over 2, well, then I'd have my original Hamiltonian. So in other words, what we're trying to say is that let's actually give these things names. Let me get a color here. Let's give these things names, okay? So I'm going to call this factor over here, I'm going to call it A, and this factor over here, I'm going to call it A dagger, all right? So these are the famous ladder operators. We'll explain that shortly, but let me just write that over here. Let's erase this Schrodinger equation. So A is simply I over m squared omega squared times p plus x, and A dagger is the exact same thing but with a minus sign for the imaginary term. Okay, so we've just defined these two operators here. There's nothing deep or profound about them yet. Okay, well, I'll motivate them soon enough. But here we're just saying that, let A be this and A dagger be that. And, we've defined them up to a constant, okay, up to a constant K. So maybe put a constant K out there as well. So, okay, so we've got this so far. So what's the big deal here? Well, the big deal is that we've been able to rewrite our Hamiltonian in terms of these ladder operators, right? That's the critical idea. So, in other words, I can rewrite my entire Hamiltonian H in terms of these ladder operators as, so H, I was able to write as A times A dagger, right? So, A times A dagger, and then plus this little factor of h bar over 2. So actually, if I just want to recover my original Hamiltonian, then I'd have to subtract this term h bar over 2, and then I'd be golden. I'd be left with my original Hamiltonian, right? So this is supposedly my Hamiltonian, right? If I take my ladder operators, multiply them, and subtract h bar over 2. Now, one more thing that I'd like to note is as follows, okay? So we want to define these ladder operators so that their commutation relationship is very simple. So I want to define the ladder operators so that their commutation is simply 1, okay? They do not commute, okay? But I want to make sure that whatever constant that they're defined up to makes it so that their commutation is 1. So how do I define the constant such that this is 1? Well, I could just go ahead and write it out as follows. Hopefully you can see what I write here. So the commutation of A with A dagger is simply A dagger minus A dagger A. And so now we're going to go ahead and compute this through. So let's go ahead and do that. So A times A dagger. So I have A right here. And remember, I have this constant up here, K. So I'm just going to factor that out over here. So I've got K squared. And then I've got I over m squared omega squared p plus x. I've got A dagger, which is, let's go back to red. That's much brighter and visible. So A is negative I over m squared omega squared p plus x. All right. and then I have minus a dagger times a. So that's going to be negative I, p plus x. And then I have, so this is a dagger. So now I'm going to write down a over here. We don't need this anymore. So a is simply I over m squared omega squared p plus x. Alrighty, so and let me erase this. So this is squared. Very good. So now we're going to just factor everything through. By the way, this constant k squared is outside of everything. So now we're going to multiply everything through and let's see what happens. So first thing I'm going to do is, let's see, I have I times I is -1 times that negative gives me positive. So I have 1 over, okay, seems like this is going to be a hassle to work out, but anyway, so I have 1 over m to the 4th omega to the 4th, which is odd, times p squared, and then plus this term, which is the momentum times the position. So I over m squared omega squared p times x, and then minus I over m squared omega squared. Here I have x times p. Okay, they do not commute. I can't simply cancel them out. And then finally plus x squared. Okay, so that is the first term due to a times a dagger. Now the second term is going to be virtually identical, but I don't want to make any mistakes, so take any shortcuts. So let's FOIL it out when in doubt. So I times I is I squared. That cancels out the negative here. So I have 1 over m to the 4th omega to the 4th p squared. And then I have this momentum times position term. So minus I over m squared omega squared p times x. And then I have x times this term. So that's going to be plus I over m squared omega squared x p. And then finally x times x, which is simply x squared, right? So this is our second term. And outside of all of this is our constant k squared. We would like this entire commutation relation to equal 1, right? That was our goal originally. So let's see what's happening here. So first of all, let's distribute out this minus sign. That's going to flip each of these signs. So this is going to be minus, and this is going to become plus. This is going to switch to minus. This switches to minus. Okay, very good. Now let's go ahead and erase these braces. No need for them anymore. And let's see what we have remaining. Okay, so first of all, let's take a look at our momentum squared terms. These seem to cancel, right? We simply have momentum squared, same factor for each. So these cancel, certainly. I have x squared minus x squared. These certainly cancel. Okay, all right. Let me delete this brace over here. Let's see if there's anything else that cancels. Not quite, maybe not quite. So here, if I factor out, hopefully you can still see down here, if I factor out I over m squared omega squared, then I get px minus xp, right? That's what I have over here. And then if I factor out the same thing, I over m squared omega squared here, I get px minus xp, right? Simply the commutation relation between between momenta and position. And then all of this is multiplied by whatever constant I have, k squared, to give me 1, to produce 1. So now let's make up some free space over here. Maybe I'll erase this. Okay. All right. So now what we're going to do is check it out. These two terms are the exact same, right? I can simply add them up. So I've got, let's use red again, since that's the only color that seems to work here. So I have k squared times 2 times I over m squared omega squared, okay, times the commutation of p and x. I shouldn't use braces here because it might confuse you with the commutation relations. And this is equal to 1, right? And so now what I'm going to do is just solve this, right? Recall that the commutation of x sub I with p sub j is ih bar delta ij. So this is going to be minus ih bar here, okay? Now I times I is -1 times negative is just 1. So I have k squared times 2 h bar over m squared omega squared is equal to 1. And now if I just solve for k squared, I obtain m squared omega squared over 2h bar. And so k is simply the square root of this. And so k is simply the square root of m squared omega squared over 2h bar. Hopefully I didn't make any mistakes. And no, that should not be m squared omega squared. That should just be m omega. So perhaps I made a slight mistake here. So this over here, a and a dagger, did I define them incorrectly? Yes. Okay, this should be just m omega, not m squared omega squared. So apologies. Okay, that's why there was a weird factor of 4 here. So apologies. This should really be m squared omega squared. So as you can see, even geniuses can make mistakes. So this should be an n and omega, m and omega. So this is our constant term. And so now we conclude, now we have, finally we have the true value for our ladder operators. Okay, so now that we know what the constant k is, we can write that our ladder operators are as follows. This is called the annihilation operator. A is simply going to be k, which is now known, m omega over 2h bar, times I over m omega p plus x. And similarly, a dagger is almost the exact same, m omega over 2h bar, but now it comes with a minus sign, right? So that is it. This is the derivation of the ladder operators, okay? So folks, that's it for this lecture. In this lecture, we derived the quantum mechanical ladder operators for a simple harmonic oscillator. And in the next lecture, we're going to really interpret this and exploit it to enforce second quantization. So once again, this entire lecture was done in one take. Maybe, depending on how I feel, I'll edit this and rewind the entire thing.